Okay, so let us revisit our story about Oddtown and Eventown. So first, Eventown. So a club must have an even number of members, and any two distinct clubs must share an even number of members, right? So it means that by definition, the block intersection matrix has even entries. But if that is the case, then if we consider it over the field of two elements, so even numbers are just zeros in Z2. So it means that M transpose times M is just zero, just the zero matrix, right? Well, but then if you think about it, so this condition that M transpose times M is zero, it implies that the orthogonal complement to the column space of M contains the column space itself. Well, if you don't understand it, maybe a better, well, a slightly different point of view of that is the following. We need to show that every entry in the column space of M is orthogonal to every entry in the column space of M, right? This is what it means. But column space is spanned by individual columns, and individual columns of V are just characteristic functions of clubs. So every column of V, it looks like zeros and ones, with ones at positions corresponding to people who are in that club, and zeros corresponding to people who are not in that club, right? And the requirement here is that all these columns are orthogonal to each other. But if all these columns are orthogonal to each other, it just by definition means that the column space V is contained in its own orthogonal complement. At the same time, we know that dimension of V plus dimension of V orthogonal complement is n, right? So, and since orthogonal complement of V contains V, right? So this whole thing is actually bigger than 2 times the dimension V. So which is how we got this inequality. 2 times dimension V, 2 times dimension V is less than or equal than M. Right? But then the dimension V itself is less than or equal than M over 2. And then you can immediately conclude that the largest possible number here is 2 to the power M over 2. Well, of integer part of M over 2. This is not really much easier than the purely combinatorial answer to this. It is possible to do it just purely combinatorially, and it's not really harder. But look at the now at the Oddtown problem. So under the Oddtown rules, so a club must have an odd number of members, and any two distinct clubs must share an even number of members, right? But these rules are kind of, by very similar logic, they imply that the block intersection matrix is just the identity matrix, right? So in this case, since it means that the M has rank n, so the number of clubs just cannot be more than M. Now it's even easier. So now it's just very, very simple. And I don't think that even if it is possible to solve the Oddtown problem combinatorially, it's much harder, right? So here linear algebra really helps a lot. Well, and the third version is even harder. I have no idea how to do the third version combinatorially. But in terms of linear algebra, it is kind of, I mean, it's not as simple, but it's doable, right? So now suppose that any two clubs share exactly lambda members. So So we consider the case lambda equal 2, right? So remember that the case that we introduced in the first in the beginning of the lecture is lambda equals 2. But generally speaking, it might not be. So now sizes of blocks are now different. So so let ki be the size of the block I. And consider again this block intersection matrix. So now let make sense. What is this? So J minus I. Recall that J is the matrix of all ones, and I is the matrix with ones on the diagonal. So J minus I is the matrix with zeros on the diagonal and ones outside the main diagonal. So it shows, and times lambda, of course, we will have lambdas outside the main diagonal. So what does it tell us? So this part just gives us the rule under which the intersection of every two clubs should, so every two clubs should share exactly lambda members in common, right? And this k here, so this k is the diagonal matrix that with sizes of the blocks on the diagonal, right? So this is also a part of the definition. But then if you the trick here is to have any non-zero vector x. Assume that x is a non-zero vector, and then we are going to, so if x is not zero, then we are going to try to compute the dot product of mx and mx. And then we will see that this dot product cannot be zero. So that there is an explanation that you can read. But then it really means the null space of M is just zero. And if the null space of M is just zero, so M has the full rank, and again, N has to be less than or equal to M. Okay, so, and again, at most 2019 clubs can be formed. Forming precisely 2019 clubs is a different story. To be honest, I don't know if it is possible. So I couldn't come up with a specific example.